Hi, welcome to Digital Dialogs, your compact conversations on the future of technology. And we're back with season 3. Can you imagine? And for this, we have a special expert guest today. And we're actually going to talk a really amazing topic. But first of all, my name is Rene from Reply. And what we're going to talk about is trailblazing robotics at NASA, shaping the future of autonomous space exploration. What a title, isn't it? And for this, we have also a special expert guest, Dr. Julia Badger. Hi, Julia. How are you today?
Hey, Renee. I'm well. Thank you.
Awesome. First, thanks of all for agreeing to be part of our podcast here. And can you share a little bit about your background and your journey into robotics and autonomous systems at NASA?
Absolutely. Well, I'll take you way back. When I was in high school, I had a project where I built a robot and I thought it was pretty much the coolest thing ever. And so I was already obsessed with space. I thought space robots was absolutely where I needed to go. So I went to Purdue University for my undergraduate degree. I got a co-op, a returning internship essentially with NASA during that. Decided I wanted to go to graduate school to get my PhD. So I went to California Institute of Technology and worked with some JPL folks while I was at Caltech, and ended up back at NASA right afterwards in the robotics technology branch. So I've been working rovers, I've worked humanoids, I've been spending the last little bit trying to make a spacecraft called the Gateway, which will be in orbit around the moon, a robot, if you will, by letting it be autonomous, separated from earthbound control. So lots of fun stuff.
So it's like a space drone.
Exactly.
Awesome. Autonomous space drones, that's pretty awesome. And the good thing is in space we don't have regulations like we have on Earth, right? Like you cannot fly your drone here, you cannot fly it there. It's the wild space west.
You would be surprised. It gets kind of crowded out there, so it's a little different. But there's absolutely a lot of standards and things that we do need to follow to make sure that we're being safe for the people on Earth first and foremost, but also all the infrastructure that we have out there. For example, nobody wants their GPS satellite to go down, right?
Oh yes, yeah, I can imagine. And then we also have SpaceX up there with like basically building a grid where you need to pass through a slot or something. I don't know, but
Yeah, no, it's like the Wall-E, right, where they have everything around the Earth.
yes. Yeah, that's a good point. Yeah, like brings back good memories. So thanks for your introduction and definitely impressive background. And I love when you said like the kind of the flame got ignited during your high school years or back in the days when you were a student.
Right.
And I think that's a success story of many people that they got this little seed. Right. That's why I'm always so. I mean, I have 5 kids, right? So I have a bunch of school kids. I'm
Wow.
really excited always about education, and and igniting and giving the passion, like and you had that journey, right? So that's really cool.
Absolutely. Yeah.
Okay, so let's talk about some of your work you're actually doing. I know in NASA's missions, like you said, right? There's of course a lot of regulations and a lot of processes you have to follow because you actually need to have probably, well, that's rocket science in the end, right? And you need to have unparalleled reliability and resilience. Like that's for sure, right? You cannot just go
Right.
up there and fix something and so on,
Right.
right? So you need to have that really built from the ground up. And so could you share how your expertise in also formal methods and advanced control is helping shape these next generation robotic systems for space?
Yeah, absolutely. Yeah, so the my PhD thesis was on basically formal methods in robotics. So when I came to NASA, I had a lot of ideas about how we could do that. One of the biggest things that we do when we send up a robot or we send up a spacecraft is we have to make sure that it's going to perform as expected. We have this concept that's called test like you fly. So doing the best that we can. A lot of times we're building one of things. For example, the habitation module that we're building right now for Gateway, there's going to be one of them. So it's very important that we do as much testing as we can to make sure that it works. Testing is incomplete, right? You try to find test cases that kind of capture the bounding conditions for how it's going to operate. But especially when you're thinking about software or, robots or anything that's kind of autonomous. So, for example, we have autonomous fault management on board. Anything
Mhm.
that might be dealing with situations that you didn't think of, the unknown unknowns, if you will, those are really hard to test for because you don't know them. Like the whole definition of them is that we don't know that they're going to happen. There are folks who've done research here at NASA on the International Space Station and the payloads and all of the systems they have on board. And they've recorded how many times we've had an error that we didn't anticipate. It was an unknown unknown, and it happens dozens of times a year. It's reduced as the age of the ISS has increased, right? But there's absolutely these are things that happen. So formal methods are a way to try to exhaustively go through the state space of whatever system that you might have to understand if you can reach these bad things. Of course, they're limited by how you describe your system, how accurate you can describe your system, and then how much processing it takes to go through basically all of the different things that could happen. But more formal methods does it in kind of a nice way. And so to actually apply formal methods to a system, you have to kind of be creative about it. So in a couple of ways we've done it. We've used some model checking for the kind of the beginning of your overall system, your requirement space. So understanding if I'm asking my designers to do something that is just fundamentally incorrect or conflicting. We've done a little bit of work of how do we specify those requirements and how do we make sure the requirements are self-consistent and satisfiable, essentially. Then we've also kind of gone on the back end where we've said, we are going to put this robot or spacecraft up there, and we want to make sure that this condition, if we ever see this condition, we shouldn't see it, but this would be out of bounds. If we do see this, we want to react to it. And so we use a runtime monitoring capability that essentially does that same thing, where on board it's checking specifications that are formal to make sure that we don't get into those situations and sending verdicts that indicate we are there, and then we would react to those verdicts if so. And so it's actually kind of a fun application. We've never applied this to a human spacecraft before, so we're breaking ground there.
That's quite impressive. And of course, like you said, your background also with formal methods is helping in that space quite a bit. So yeah, like I said, it's really good to see these being applied to these complex systems, because that's what also your example with ISS was great, right? You try to find out everything in advance, but these are such sophisticated, complex system. It's like you might even call those chaotic systems, although they are not. But there's so many unknowns, and things can happen. And then you're flying at a crazy speed through space, and what can go wrong, right? What could possibly go wrong? Yeah. What are some of the key lessons you've learned about guiding innovation while meeting mission critical demands at NASA? And maybe you can also share about some recent examples like Project Gateway. Maybe you can start just explaining for our audience that are maybe not too familiar what Project Gateway is, and what you're doing there. And then, like I said, maybe you can share some lessons learned how you meet these mission critical demands.
Absolutely. Yeah. So some background on Gateway. Gateway is an international cooperation. It's going to be a space station that will be in orbit around the moon. So for our Artemis campaign, which is this whole set of things that will be flying all at the same time, what we're planning on doing is we're taking humans from Earth, we're sticking them in a capsule, we're flying them to the moon. They aren't going to land right away in that capsule. That capsule is really just for Earth transit, and so it's going to dock to the space station, the Gateway, which is in orbit around the moon. It'll have other things there, like a logistics module for their spacesuits. It'll have a landing system so that spacecraft is meant for on orbit to moon surface transit only. So they'll transfer into that. They'll do their surface operations, come back to Gateway, get back into their trip home, their Orion capsule. And so Gateway is going to be uncrewed for much of its life. It's going to hang out, be there, do science all by itself. When people are going to do that moon mission, they'll be living in the Gateway for 1 to 2 months out of the year. And so it's got to be able to support quite a bit of things. The way that we do operations right now for the International Space Station is we have folks in mission control 24/7, 365, always caretaking, sending up hundreds of commands per day to make sure that the ISS does what it needs to do. But since Gateway is going to be flying while many other spacecraft are flying, what we need to do is break that paradigm and make sure that Gateway can take care of itself for up to 3 weeks at a time, actually, without earthbound control. So we're building, my team is building a system called the Vehicle Systems Manager that takes all those hundreds of commands that the ISS operators send per day from the ground and sticking them on board in this system. So it does fault management, timeline management, execution of tasks, resource management, all of those types of things. This is the first time we've flown several of the things that I just said from a technology standpoint. It's taken decades to get to the point where we can take very low technology readiness level types of things, university research, low government lab type of research, and then actually apply it to a real system. It's actually one of my passions to kind of hit that valley of death and push the technology development like along that curve. And it really takes a lot of focus on how do we define our system. So the definition of your system, if you can do that in a nice, simple, and you maybe even going back to the formal methods, if you can do it in a way that structures your problem so that things can be like maybe broken apart. So for VSM, we're distributing it across the entire gateway. So lots of different computers will be involved in identifying and dealing with faults. If you can structure that problem appropriately, you can actually start really thinking about feasible solutions to stuff. So that's what we've done, is that we developed an architecture, and now we're pushing that forward. And if I can keep going for just a second, that all kind of came from building Robonaut, which was this humanoid robot that we sent up to the International Space Station. It's very complicated. It has 57 degrees of freedom. It can walk. It has fingers and hands. It has cameras and torque sensors, and there's just a lot of information going on there. We realized we couldn't kind of joystick it from the ground. We couldn't teleoperate it. We had to let it have its intelligence on its own because the time delay was too great, and just having to send that much telemetry back and forth wasn't feasible. And so we did sort of the same thing with that. We distributed control across all of the joints. We had high-level control kind of in its core chassis of computers, but that was at a lower rate and was doing less, and we pushed more kind of smarts down to the joints. We're doing the same sort of thing with the gateway, with new technologies, and making things work that way.
That's really impressive, and I'm glad that you actually took a couple of seconds more to talk about the humanoid robot that was up in the space station, because obviously that's also an interesting aspect, I think. When we talk about these further missions, obviously the plan is that you also laid out with the Gateway space station, basically orbiting the moon, is to bring people back on the moon, and astronauts back on the moon, obviously. Mm-hmm. So that's a great cause. But I was wondering, maybe also humanoid robots could make a lot of sense to actually go down to the surface of the moon and help to build build stations or do things like this. Is it also something you're thinking about?
So humanoids, not right now. Humanoids still aren't quite to the level of independence and capability. And I've worked on this. You can't walk on the moon. So you'd have to have something else. So if you watch the Apollo astronauts, they bound. It's actually the level of gravity. Physics makes it more, it takes more energy to walk than it is to kind of like leap, right? So we would probably want robots that could roll. So there are a few. We're sending robotic landers through the CLIPS project right now. There's actually 2 that will land on the moon next month. And so those are kind of robotic landers that are going to start looking for sites for humans to land and start figuring out volatiles. There's Viper, who's trying to find the ice at the bottom of permanently shadowed craters on the moon that hopefully will get some partnership and be sent to the moon soon. And then there's actually the Lunar Terrain Vehicle, that we have lots of vendors working on, and JAXA as well is going to participate in some of that. And these are vehicles that are going to be able to self-position, but also carry astronauts. So they're kind of the autonomous cars, if you will, for the moon surface. So those are all robots that we are planning on doing as part of Artemis. Humanoids will come later.
Gotcha. It's like the lunar robo taxi then.
Right.
That's pretty awesome. In fact, like just as an anecdote, there is like, I'm born and raised in former GDR, right? So there is obviously, and I'm glad that's not existing anymore, because otherwise I wouldn't be here working for the company I work for or being able to interview you. So I'm really thankful for my parents' generation that went peacefully to the streets. But what I'm trying to say is there is a fun little series they do on Instagram. It's called GDR is DDR in German. And so it's DDR Mondbasis. And so it's so hilarious. They're using AI generated videos and under the hypothesis that the GDR built a moon base in the 70s or 80s. And they make all these ridiculously funny clips. And for example, not sure how much you're familiar with that, but in GDR, we had like a Trabant, which was a car. It is mainly made out of paper in the end. It was like a little car. And so like in that series, they had a Trabant on the moon as a moon vehicle. I have to send you the link. It's too hilarious. But yeah, it's really funny because it also is done in this style of the 70s and so on, with the people's clothing and so on. It's really hilarious. That's what I really love. But sorry, I had this in mind when you talked about the lunar vehicle. I was just thinking, yeah, they had the Trabant. Yeah, but the Trabant is actually the moon, right? Kind of a thing, like the Latin word. But so coming back to more serious stuff, obviously, like you said, yeah, totally right. Like a whole different gravity on these, like moon or like let's say Mars or whatever you want. Of course, there's different gravity. So yeah, I mean, we saw that with the drone, right? That came with the rover on Mars.
Yeah, which was amazing. Yeah.
It's a huge scientific and engineering, of course, right? The engineering part is really impressive as well. And yeah, I mean, they managed to fly a drone on Mars. Like, how crazy is that, right?
That's so cool.
Without having that gravity to test in advance, actually. So that's a really impressive part. I think that's also an interesting part when we think about sim to reality, right? Simulating these environments and these sceneries in, let's say, NVIDIA Omniverse or other solutions out there, but running these large-scale simulations and also training for these autonomous vehicles, robots, whatever you want to call it, and then applying that into the real world. And I guess that's also something you're leveraging is like, of course, lots of simulations in advance, right?
Yeah, it's actually kind of interesting because obviously people are working on autonomous vehicles here, right? There's a lot of kind of similarity of the concept of what we're doing, but we have a lot of constraints in space that we don't have on the ground here on Earth. For example, a lot of the times the autonomous vehicle companies, they will send out, they'll put like cameras on all these cars and they'll send out and they'll have just thousands of hours of video that then they'll go and train algorithms to identify pedestrians or this, that, or the other thing. So that's great. And you can do that here. Once we go to the moon, we will get video from like one camera and it'll be kind of choppy because there's radiation and the lighting is completely different. Like there's no air, so nothing diffuses. It's stark. There's no roads. There's no pedestrians. There's all these things that are just very different. And so it's almost that we can't use the same, there's a lot of places where we cannot use the same technologies just altogether. So even though, there's a lot of stuff going on here that you'd think, oh, this is applicable both ways, you really have to kind of pick apart the pieces of technology that do apply each way, right? From the Earth to the moon and then from the moon back to the Earth. Not that it's wasted, right? I think that when we learn something on the Earth, we can apply that kind of concept to the situation on the moon and vice versa. But it's not a direct one-to-one type of thing. We're actually solving very different problems.
Yeah, yeah. And alluding to what you said is like that, some of the technology that is being developed with autonomous systems obviously can also be applied on other like the moon or other surfaces, whatever. Um, so what do you think? But there's also like we don't just see it with autonomous vehicle navigation, with AMR and drones and so on, but we also see that with humanoid robots. I mean,
Hmm.
if you look around, there's so much progress happening, and I think
Absolutely.
also the simulation aspect is really important to actually get these robots in a working way that we can generally use them. Like I always keep on saying, is like we live in a world built by humans for humans, and
Hmm.
so these robotic systems have to adapt to those. And I think, Turing test was already passed, right? With GPT-4, like the OpenAI model GPT-4, they did a study in May 2024, so a little bit more than a half a year ago. And they found out that the majority of people cannot distinguish if they're talking with GPT-4 or with a human. So
Hmm.
basically, Turing test passed. And but you know what the real Turing test will be? If I can put a humanoid robot into a Fiat 500 or whatever old timer from the 50s, from the 1950s, and this humanoid robot can actually drive me in that old timer car, right? That's what true autonomy. You know how I call this? Because Fiat 500 was built in Turin in Italy, and so
Uh-huh.
it's the Torino test of AI, obviously.
I love it.
So that's the final test we gotta see. Long story short, I actually wanted to ask you a final question. Sorry, but we're having good fun here, so that's good. Um, so humanoid robots obviously are very pushed forward on in the technology realm this year massively, I think,
Hmm.
and I think this is also important if we maybe not for the moon, but if we think further out, like let's say Mars or other planets that we want to send humans to. I mean, of course, it has to have a surface first of all, or a solid surface, which is not common with many planets. But long story short, do you think like humanoid robots will also play an essential role for, I don't know how you call it, but more long-term space travel because
Yeah.
they have batteries in the end, right?
Absolutely. So, like I said, the moon you can't walk on. That doesn't mean you can't have an upper body humanoid. We actually do mobile manipulators concepts for these assets that we're essentially emplacing before we can send people, like Gateway. Gateway will be uncrewed for quite a while before we have humans on board. Things will still break. We will still need manipulation and inspection and different things that humans can do. And building kind of the robot to accommodate the human's world, like you said, is going to be essential anywhere. Obviously, there are things we can do to make it easier for a robot, and we are trying to do that even now with Gateway. But as we think about, so our Artemis program is a part of the Moon to Mars initiative. We are thinking Mars forward, with the autonomy with Gateway, with our rovers on the moon's surface, and with the humanoid and robotics research that we do at NASA even today. So we have the Valkyrie robot.
Mm-hmm.
She's an upper body humanoid and a lower body humanoid. She walks. Um, the Martian surface is 1/3 gravity. You can walk in 1/3 gravity. That's enough gravity to walk in, right? So if having the habitats that we will probably send and build on Mars' surface before we have humans there for their stay, that will need to be robotically situated. And then also there needs to be a robotic caretaker for that too. So we're absolutely still thinking about those manipulators. We're still thinking humanoids. We're still thinking walking even here, because we are really very much thinking about 2030s being going to Mars, right? Sending folks to
Yeah.
Mars.
Yeah, and it's also impressive when you say 2030s, right? When we look into space programs, like you said, also initially, like it's dealing with decades, and
Mhm.
that's the timeline we're looking at, right? Like uncommon for folks that come from consulting or something, because it's always, yeah. Well, I mean, we also think forward, but it's mainly like what's going to happen in the next couple of weeks or months or something, right? And
Mhm.
it's like for you, it's of course decades, and that's impressive. So you're basically testing also with Gateway the principles and all of that, and then we have the moon ready. Once we're check moon is ready, let's go to the next one, right?
Right.
So,
Absolutely.
but But you're moving in parallel with these programs, right? If we look at the NASA side or other places, you can see a bunch of that in public information, which is great, by the way. There's so much great information also. Like I also said, education is very near and dear to my heart. Also, as NASA does in terms of education, bringing out all of this public information is always great. So that's definitely also very much appreciated. And yeah, when we see these programs are actually running in parallel mostly.
Yeah.
Yeah.
Yeah, and the thing with Gateway is that it's from literally across the world. There is a ton of European contributions to Gateway. So absolutely, you should look up and see how your country really is contributing, because everyone is.
Yes, yeah. That's a good, impressive part. I was once lucky to give a keynote at the ESA, at the European Space Agency in Frascati near Rome, where they have the Earth Observation Center mainly. And it was great day, and also geeking out with lots of good people there. And yeah, you really see the kind of the kind of diversity there. You have coming from all over the place people, right? You have, and that's really, I love that aspect, because bringing in these diverse minds, they all have different backgrounds and so on, but also different history and different culture and so on. It's like you build the best solutions with that setup, right?
Absolutely.
And so really appreciate that. Well, Julia, we're actually at the end of the show, because we don't want to keep it too long for our audience that actually be able to listen to it. But if there's anything you want to say finally, please go ahead.
Just thanks for having me. I think space is fun, and I think there's a lot to look forward to in it. So keep your eyes to the sky. Thanks for having me.
Awesome. Thank you so much, Julia, for joining us and sharing your insights and taking us through the journey through NASA's robotic evolution and what's going to happen there. That is very much appreciated. And thanks everyone for tuning in to Digital Dialogues, your compact conversations on the future of technology. Watch our blog, follow social media, and subscribe to our podcast channel so you never miss an upcoming episode. You find us on all the popular podcast platforms, and obviously you can always go to reply.com to check out any previous or current episodes. Until then, take care and see you soon. Bye-bye.